Hey guys, this is Hadi Atayi, and I'm going to, talk about and have a series of courses addressing deep learning, and I'm going to focus on theory and the math behind it rather than implementation because I believe implementing it is not that difficult. What's really important is understanding the theory and the math that goes behind the scenes. Therefore, I'm going to focus on that and uh, start from the very basic ideas behind the fundamental and the basic principles of machine learning. The first thing I'm going to talk about is learning algorithm. Um, so in the context of machine learning algorithm, uh, the learning algorithm is the one that can improve its behavior, meaning the model's behavior, by using data. But what exactly does learning mean? Mitchell, in his work in 1997, offers a well-known definition, and it's very precise. So we're talking about learning algorithm here. So he says a program is considered to learn from an experience E. Right? So he says a program is said to learn from experience E regarding a set of tasks T and a performance measure P if its ability to perform those tasks as evaluated by P gets better with experience E. Okay, I'm going to read one more time. A program is considered to learn from an experience E regarding a set of tasks T and a performance measure P if its ability to perform those tasks as evaluated by P gets better with experience E. So there are many possible forms of experience, many kinds of tasks, and many ways to measure performance. Rather than giving strict definitions for each of these, this series of courses instead provides intuitive explanation and examples to illustrate the various types of tasks, performance criteria, and sources of experience that machine learning methods can use. So we talked about the definition. Now the first thing we need to understand is what is this task T that we talked about. Machine learning allows us to address problems that are too complex for traditional manually written programs. Scientifically and philosophically, it is compelling because understanding machine learning helps us understand the fundamental principles of intelligence itself. In this formal sense of the word task, the act of learning is not the task. Okay, so the act of learning is not the task. Learning is the method we use to gain the ability to perform the task. For example, if we want a robot to walk, then walking is the task. We may design a learning algorithm that teaches the robot to walk, or we could attempt to hard-code the walking behavior by hand. Machine learning tasks are usually described in terms of how a system should process an example. An example is a collection of features. So any example that you can think of, whether a sentence, an image, is a collection of features, which are quantitative measurements of some objects or event. We typically represent an example as a vector. So here we're talking about task. task T. Now, let me bring this. So for the task T, any example is a vector, maybe n-dimensional vector, right? Each component X corresponds to a particular feature. For instance, in an image, the features are typically the pixel intensity value. So there are many kinds of tasks that machine learning can address. Some of the most common ones that we are going to talk about, we'll list them and kind of describe them. The first one is classification, right? So classification is the first one we are going to talk about. So classification, in a classification task, the algorithm must determine which of k categories an input belongs to. The goal is usually to learn a function. The function usually is described as such. So we have a function f. Its job is to map any vector example x to a set of to one of the classes that belong, k classes that are already predefined. Here, y is f of x, where x is the input, right? This function, f of x, assigns the example x to a category labeled by a numeric code y. In other variations, the model may output an entire probability distribution over the classes. A typical example is object recognition, where the input is an image represented by pixel values, and the output is a label identifying the object in the image. For instance, an instance would be the Willow Garage PR2 robot, which is capable of identifying different beverages and delivering them to users on request. So this is an older robot. So right now we have much more advanced robots. So modern object recognition is most effectively handled using deep learning. The same core technology is used. The same core technology is used for another applications. For instance, facial recognition, which has so many different applications, and also powers automatic photo tagging and enables computers to interact more naturally with people. So the other task that's similar to classification is classification with missing inputs. So classification becomes more difficult when the algorithm cannot rely on receiving every feature in the input vector, so thus missing inputs. Normally, the learning algorithms need to learn a single function that maps a complete input vector to a class label. But if some inputs might be missing, the model must effectively learn many classification functions, one for every possible pattern of missing feature. This scenario is common in areas like medical diagnosis, where certain tests may be costly or invasive and therefore not always available. A practical way to handle this large number of possible missing input situations is to learn a probability distribution over all variables. The classifier can then make predictions by marginalizing out the missing features. So if we have n input variables, so if we have n input variables, how many subsets of missing data could we have? We could have 2 to the power of n possible subsets. Missing data. So this is the maximum number of subsets of missing data. And this would represent 2 to the power of n potential classification functions. Right? However, by learning a single model of the joint probability distribution, the algorithm can derive all these functions when needed. Many other machine learning tasks can be extended to handle missing inputs in a similar way. Classification under missing data is just one illustration of this broader capability. Another very important task so how do we, okay, this works. Another very important task is a regression. So regression, in a regression problem, the goal is to predict a numerical value from a given input. To accomplish this, the learning algorithm must learn a function. So we learn a function f that maps an input to an output. The key point is that the output is a continuous value. Regression is similar to classification, but instead of assigning an input to one of several categories, just as we did in classification, the model outputs a continuous number. Examples would be estimating the housing price, like what Zillow does, Redfin does, estimating the expected insurance claim amount for a customer, or forecasting future stock prices. Tasks that are also important in algorithmic trading. Another task is transcription. It's not just, voice to text, but that's what we think about when we talk about transcription, voice to text. But transcription generally requires the model to take an unstructured representation of data and convert it into a sequence of discrete symbols. Optical character recognition is a common example. The system receives an image. So the system receives an image of text and outputs the corresponding characters, for instance, in ASCII or Unicode. Another example is Google Street View, which uses deep learning to read house numbers in this way. Speech recognition is another example, where an audio waveform as an input is transformed into a sequence of characters or word identifiers. Deep learning is central to modern speech recognition systems used by companies such as, all these companies that you know of, Microsoft, IBM, Google, whatnot. So another important task within machine learning is machine translation. So you might say, what's the difference between transcription and translation? The transcription, as we said, uses an unstructured representation of data as input, but in translation is more or less as a structured, not exactly structured data, but is more structured. What do I mean by that? It means that the input is a sequence of symbols in one language, and the task is to generate a correspondence sequence in another language. Classic case would be translating from English to French or any other language. As you know, the LLM models today have achieved, very advanced milestones in terms of translating between different languages. Another machine learning task is structured output. So the structured output requires producing multiple related values arranged in a vector or other structured format. This broad category includes transcription, translation. So we're talking about this structured output task includes transcription and translation, and many other additional tasks. One example is syntactic parsing, in which a sentence is mapped to a tree describing its grammatical structure, with nodes labeled as nouns, verbs, and adverbs, and so on. Another example is semantic segmentation, where each pixel in an image is assigned to a specific category. Deep learning can also be applied to tasks like identifying roads in aerial imagery. In other structured output tasks, the output format may differ significantly from the input. For instance, in image captioning, the model receives an image and generates a natural language description of it. These tasks are considered structured because the output consists of multiple interdependent elements. The words must form a coherent, grammatically correct sentence.